Okay. Okay. Hello, I'm Andreu. I'm an industrial PhD here in UPC and Automatic TV, there in MediaPro. And I'm going to present you to talk about the object detection task. So these slides and everything has made by Amaya and Miriam, who has very nice lectures online. So if you want to check them out, they are very good. And well, let me start. So object detection is a traditional task in computer vision, and it's basically the task of detecting all the objects in an image and assigning them a bounding box and a label. Okay. So real quick, now you have already done the image classification problem with Xavi, and we will treat the object detection as a similar task. So instead of having to classify the whole image, as for instance dog or whatever, we will classify each crop of an image. We will take some crops and classify them, and to have all the detections in the image, right? So, for instance, we try to classify this, and our classifier says, okay, there's nothing here, it's background, so it's okay, it's correct. When it stands here, it classifies a cat, so okay, it's also correct. But using the same approach, the same sliding window approach, so this is a dog? No, right? Because the bounding box doesn't fill the dog. So the classifier correctly says, okay, this is not a dog. So what do we need in order to detect every object in an image? So we will need several bounding boxes around all the objects, all the possible objects, right? So we would have to have many positions and many scales and many aspect ratios. Okay? So for instance, this cat, okay, we had the correct scale and bounding box for this cat, but not for the dog, right? So if you have very fast classifier, you could use this technique. Just try blindly every position and then classify every position. And then you would have where are the objects located. But as we are using deep neural networks, and they are quite expensive in terms of computation, so we cannot okay, now we can, and later on I will explain you, but let's say that we cannot test every location, right? So the thing we should do here is to choose wisely which regions are we going to test instead of testing everything blindly, okay? Before that, I will just present you some data sets that are used for object detection, which are Pascal, which has 20 categories, and more bigger data sets like Coco and ImageNet. Okay, so if you want to play with them, you have them here. In object detection, we will differentiate between two categories. The first one is the proposal-based methods, which are based on having an algorithm that will propose these bounding boxes instead of having that explosion of bounding boxes we saw, and the proposal-free methods that they don't rely on any methods that makes the proposals. So for the first thing, the proposal methods. So the idea is to find some kind of blobby regions that allow us to not to have to check for all the places and different aspect ratios of the bounding boxes for the whole image. So for instance, in this case, we would take the dog, the cat, some flowers, maybe the eyes, the nose, but we would not take, for instance, this patch here or another patch that would only add a computational thing, and we don't really want that, right? So how to make these regions proposals? These regions proposal can be done with selective search or MCG, multi-scale convolutional grouping, which are segmentation, hierarchical segmentation tasks, or methods, sorry. And in this case, for instance, if we want to get the cow or the post or everything like that, we just have to group superpixels, which are unions of pixels, and we keep grouping them in a hierarchical manner, and then we start taking some regions of interest, like this cow here, it's maybe some region here, and this cow here is another region, okay? So basically, you take the regions of interest and then take the bounding box around them and use it as a proposal, yeah? So the first one that used the neural nets for this object detection task was RCNN, which stands for Region Convolutional Neural Network, and it was made to 2014 with Girbau et al. And what they did, basically, they extract region proposals with that method that I just told you, and then for every region proposal, they classified with a neural network which class was it, okay? They had to do this wrapping thing because you have some fully connected layers in the end, so you have to have like the same input, so the program does not explode, right? So basically, it's this idea. Oh yeah, sorry. Finally, instead of like having a softmax classifier or a multi-layer perceptron, they trained an SVM, which stands for Support Vector Machine. Okay. And yeah, this is what you would like to have, but instead you have like 2,000 proposals, right? From this proposal algorithm. So for every proposal, you have to have an output. Okay. What do you do to like have this nice output instead of this one? You do some score thresholding, like for instance, this is not a TV, right? So the probability of being a TV, okay, maybe you will assign a probability, it will be like the highest one, but it will not be high, maybe 0.0.3, okay? So you just take it out. And also you do the non-maximum suppression, which is basically that you take, if you have several detections here for horse, because you would have like several proposals for horse, you take the one with the highest score and then just erase the other ones based on intersection over union or some other thing, okay? So yeah, basically they beat everyone else with this. So these two didn't use deep neural networks, and well, this is the same, but with some other characteristics, like this BGG16 that you saw that Xavi explained you. So yeah, they just beat everyone. But the problems that it had is like it's slow at test time, because for every region proposal you have to do an inference of the network, right? And also the ESVM does not allow backpropagation, so the weights of the network are fixed. So the weights of the network were not like actually actualized with the results of the network. So they like extended the work into a fast RCNN, which tries to solve the two problems. The first one, which is slow at test time, is because you had to do like many inferences of for every region proposal. And in this case, what you do is just do an inference of the image directly, and then instead of like cropping in the image and then passing through the network, they crop into directly into the feature space. Okay. To do so we have two fully connected layers. Do you remember? And like we should transform somehow this into like warp it somehow so that it fits into the two fully connected layers. Okay. How do they do that? With a ROI pooling layer that stands for Region of Interest Pooling Layer, where basically you have the activation map here, and then you map the object proposal that you had to the activation map, and then let's imagine that we want a 5x5 grid, so they just match it there, and they did a max pooling in order to keep the ratio they wanted. So you can connect it to the fully connected layers, and everything works. Okay. The second problem was that if they trained the ESVMs, they couldn't like backpropagate it through the network. So what they did is to add a softmax layer here that it was just assigned a probability that could be trained in an end-to-end fashion, and then a bounding box regressor that adapted like the object proposals to actually fit the object that they want. So with these two modifications, they passed from RCNN to fast RCNN, which is like fast. And yeah, but the thing is that they had another problem, right? You see here the numbers are very beautiful, but it had a problem, which is that it still relied on object proposals, and another algorithm to generate object proposals. And this algorithm, like before, okay, before it was 47 seconds, and it didn't matter that much, like 2 seconds or not that much. But from 0.32 to 2 seconds, like it matters a lot, right? So to solve this task, they proposed the faster RCNN, which is basically the same, like this is the faster CNN, but they proposed this region proposal network. This region proposal network is a network inside a network that what does is to propose regions based on a deep learning architecture, right? So, so that they could train it like end to end, and it will be faster. How does this region proposal network work? So basically, what you have, this is the feature map, like you pass through the deep neural network and you have a feature map, and then in that feature map you just do a sliding window with several anchor boxes. What are these anchor boxes? These anchor boxes are used to not to have to invent like the bounding box from zero. So instead of like having to invent like, I don't know, 1 point here, if this is 1.5, you only have to extract 0.5, right? So they say the network converged better with these anchor boxes here. So for with a sliding window, what you do is this: you try every anchor box, and from every anchor box, you give a certain objectness score, which is this 2 score. Like K stands for K anchor boxes. Don't imagine that it's 2000. I imagined it, and I was like, what? And it will stand for it's an object or not. And then the 2 K coordinates for every anchor box, we will have a coordinate, like a center and a width and a height. So with this, they have, well, they had everything here. They didn't have to rely on an algorithm like that, external algorithm for generating these proposals. And they had everything end-to-end trainable, very fast, and very nice, okay? Finally, well, they added some module, some branch, extra branch, that instead of only doing the detection, it also did the segmentation of the image. And basically, they saw that training for both segmentation and detection, it helped both tasks at the same time, both improved. So they have a very nice Git. If you want to check, it's quite nice, if you're interested. Okay, so the proposal-based methods were based basically on that you had some object proposals, and then you classify each object, the proposal, passing it through the network, okay? So let's see what the proposal-free methods are. So we had this problem that, that we had like many bounding boxes, and we didn't have the computational capacity to handle them. But now the hardware improved a lot, and it's able to parallelize the computation. So now this can be used, okay? This guy, Joseph Redmond, did the YOLO, you only look once, and that does both things at the same time. It gives a class probability for every like place in the image, and also gives a bounding box regression. How do they do that? Basically, they have like a a convolutional neural network, here a fully connected layer, and then a 7 by 7 by 30, that now I'm going to explain what it means, output, okay? And then for this output, for this output, which is this one, they give two possible bounding boxes, which have some probability of being an object, and x, y, width, and height, and another bounding box. And for every cell in the grid, they give the probability of the conditional probability of being a certain class given their objectness. So they used two bounding boxes, they say, because in training time they used they assigned a bounding box to types of objects and other bounding box to other types of objects. So they say that both bounding boxes like learn somehow the appearance of the objects in the data set. So after them came the single-shot multi-box detector, which like did basically the same but in multi-scale. Right here, we saw that YOLO just outputs the detections on like the last layer, and the SSD outputs at multiple scales. So for instance, SSD would be better on smaller objects, right? Because if you come to here, you have many max poolings, and the field of view of the neurons here, they like tend to see bigger objects, and here they can recognize like simple patterns and smaller objects. So yeah, if you see the MAP, this is 72 against 63, so it worked quite much better. But then YOLO did the version 2, which is YOLO 9000, which basically they they did this ablation study, which they tried many state-of-the-art things. But I think a big thing that they did, like maybe it went worse, but making the network fully convolutional and making use of the anchor boxes, later on it helped a lot, I think. Making something fully convolutional means that you don't have to think about the image input size, because the network is fully convolutional. So it's all based on convolutional filters, right? So it's very nice. And finally, the YOLO version 3, which works at multi-scale. It has like more things. Version multi-scale, like they gave a new neural network which used the residual blocks and skip connections, and yeah, it works quite nice. They also have like the Git repo, and also yeah, they made it all in C, so it's quite fast. But if you want to change something from this architecture, it's a little bit of a nightmare. And finally, I'll talk about RetinaNet, which is made also by the guys from RCNN and all that. Which, well, the architecture itself, it uses a feature pyramid net. I think it's not from theirs, like it's another architecture that they took, and it's the typical like bounding box regressor and classifying. But the interesting part about the RetinaNet, in my opinion, is that they see a problem in one-stage detectors because they are much faster than the two-stage detector. But when I say two-stage detector, it's like the proposal-based methods, and one-stage detector is a free proposal methods. Okay, so yeah, the two-stage detectors work like better than the one-stage detector, but the one-stage detector goes much faster because it doesn't have to rely on this object proposal stage. So, but why it worked worse? Because in the one-stage object detector, you have all these possibilities of images that are classified as background, but they tend to like get the loss, like all the attention of the loss function, if that makes any sense. So what they say is, okay, basically, if you have like classified something correctly, just like put it, don't don't give it to the loss, okay? So basically, if you have already classified something good, then it's okay. Just don't take it into account in order to modify the weights and backpropagate the gradients. So this is, for me, it's the basic idea of this paper. It works quite fine. It's very interesting. So as an overview, you have here the inference time, and you have the YOLO and the RetinaNet. Well, it's just some numbers, but they're here for you to check if you want. So as a summary, well, I explained these proposal-based methods and proposal-free methods. And if you have any questions, I will try to answer them.